Hi, linear algebra students. So in this video of the makeup class on cross product and triple product, we're gonna see, and hopefully the last, by the way, because my plan is very simple. We're gonna see the third application, which is to test if two lines are skew or not in our tree. Okay, so this is the third application. There are 4 in total, but the fourth one, I already posted it on YouTube. Which is also mandatory, unfortunately, but it's in the supplement. I will just remind you that later. But for now, number 3, we want to test if two lines are skew or not. Okay, I need to explain myself here. Two lines are skew if they don't intersect, but they are also not parallel. And this can only happen in dimensions higher than R2. Because in R2, you know that two lines are either parallel, they intersect, or they're the same, right? So that's the only tree possibility in R2. But in R3, you could have something like this, okay? Where you have to imagine that one line is kind of on top of the other, but if you look at it from above, it's kind of crooked, right? So they are not parallel, but they also don't intersect. We call these skew lines, okay? And to verify if they are skew or not, there's actually a very simple calculation that we can do. And this is what I'm explaining here. So first of all, to see if L1 and L2 are skew, what you're going to imagine is this situation. So let's go again here, okay? So this is my green line and this is my red line. What I'm doing is I'm dropping the green line on the red line, but I'm not changing the direction vector. You see, I drop it in a way that the direction vector is unchanged, okay? And with that setup, I can make 3 vectors. I can take the direction vector that goes from here to here. I have the direction vector of my second line, L2. And I also have a vector that goes from line number 2 to line number 1. Okay, that is important. Okay, so we don't really care about what this point is, but that's it. We're going from line 2 to line 1. Okay, or vice versa, by the way. So if these lines are skew, as you can see, the triple product of Q, V1, and V2 will not be 0. So it will result here in a parallelepiped of non-zero volume. That's the idea behind the proof. Now, if L1 and L2 were parallel, so just imagine the scenario in which they are parallel. What is the problem? The problem is that in this case, the cross product of V1 and V2 will be equal to 0, forcing the triple product to also be 0. Okay? Then there's also the case in which they're not parallel, but they intersect. Okay, like this. So in this circumstance, what will happen? Well, basically the green line will replace the blue line in this scenario. We will have like 2 lines that are like this. And here I will actually sketch the situation over here to show you what's happening in reality. So here I'm dealing with the third case, okay? So the case in which they intersect. So they're not on top of each other. They're actually like this, right? They straight up intersect. So like this, okay? So L2. So we have like the same vector are available, right? You have like V1 that's gonna be like this, and V2 that's gonna be like that. Okay, but here's the big difference. It is that like if you take a vector Q, and again, let's suppose that you take it like this. Okay, let's suppose that this is your vector Q. Well, what you have to imagine is that okay, so maybe this is a little bit of a bad example, but okay, let's have the vector V like this. You can imagine translating the vector Q along the vector V. Okay, so this is like the vector V, and there you go. So this right here would be your vector Q. Okay, and you would get in a scenario in which these 3 vectors, V1, V2, and Q, are actually coplanar. They lie on the same plane. And the reason is simple. It's because if the two lines intersect, they do indeed lie in the same plane, right? So there's a plane that really just contains both lines. And what does it mean? Well, it means that the determinant of Q V1, V2 is equal to 0 because coplanar vectors are linearly dependent. And as a result, the triple product will also be 0. Okay, so let's now summarize this discussion into a test. Okay, we call this the test for skew lines. So test for skew lines. And it's very simple. It reads like this, okay? So two lines. So two lines, L1. And now let's actually write them in parametric vector form. So they will be like this. P1 plus T V1 and L2, which is going to, oh, oops, I forgot the X. Okay. So X is equal to P1 plus T V1 and L2 will be equal to P2 plus T V2. And then I need to erase the definition. And these two lines are skew if and only if the triple product of, again, like and let's color code it, okay, because I do like to color code my things. So if and only if you take the triple product of the vector Q, V1 and V2, well, obviously the V1 and the V2 like are here, and the vector Q is the subtraction of the position vector. So if and only if this triple product is not equal to 0, and where, so as I said, Q is equal to P2 minus P1. Okay. So let's erase all of this to do the example. So there we go. Example. So determine if the following two lines are skew or not. So if the following two lines are skew or not. Okay, so these two lines are given. We have L1, which is equal to X, negative 2, 1, negative 1. Plus T times, what are we going to get? 2, 3, negative 1. And L2, so very, very similar formula, but different position vector, different direction vector. So the position vector is 1, negative 1, 2, plus T times, and the direction vector is negative 1, 2, 4. All right, very similarly to the other problems in the section, the only thing you want to do is you want to engineer what you need to solve the problem. So as you can see, this is V1, we have it already. And this is V2. Okay, and the only thing that's left is we want to find Q, right? So step number 1 is to find Q. And Q, so, well, this is P1 and this is P2. So in other words, we're doing 1, negative 1, 2 minus negative 2, 1, negative 1. And what do we get out of this? We're getting 3, -2, and 3. So this is step number 1. Now, step number 2, we're going to do it in black, let's say. We compute Q dot V1 dot V2. Let's actually color code. Cross, sorry about that. So there you go. So we go like this, like that's it, Q. And then we have V1, V1, and V2. Okay, so one thing that you could do and that you should never do, okay, is to actually calculate the cross product. And once you're done, calculate the dot product, okay? But you should never do that unless you already have the cross product. Okay, so what you should do instead is to really find the determinant using these 3 as columns. So in other words, 3, -2, 3. Then V1 is this guy, so 2, 3, -1. And then finally this one, so we have -1, 2, and 4. All right. So the rest is calculations, right? So you know how to calculate the determinant. I will choose to cofactor expand with this entry over here. But it means that I will eliminate, like I will do row 1 is row 1 plus 2, row 3, and row 2 becomes row 2 plus 3, row 3. Okay? So I will increase my numbers, but I will make the calculation simpler afterwards. So I have like 3, -1, and 4 are actually, yeah, let's stop the color coding at this point because I'm just calculating a determinant. So, all right. So this, then we have 9 here. Wait, yes, we have 9. We have 0, and we have 7. Then we're going to have plus 3, row 3. So -2 plus 9 is 7. This is going to be 0. And this is going to be, okay, 12, 14. Okay. Now, before, okay, so let's actually do the cofactor expansion here because like we're not losing anything, right? So we're having like plus, minus, plus. Okay, so which means that we have the negative of -1 times the determinant of, and it's going to be 9, 7, 7, 14. Okay, and as you can see, we're kind of almost done. So it's going to be 1. And by the way, as you can see, whenever you have like a scalar multiple like this, let's take it out, right? You have like 7, 14. So let's take out the 7. And then we have a much simpler determinant to compute. We have 9, 7, 1, 2. Okay, so overall 7 multiplied by 18 minus 7, which gives us 11. So this calculation gives us 77. And because it is not 0, it means that L1 and L2 are skew. So L1 and L2 are skew. All right, so before leaving you, you have other videos, unfortunately, to watch. It is the 4th application, which is the distance between 2 skew lines. Okay, so now that we determined that these 2 lines are skew, in the next couple of videos, we will figure out how to find the distance between these 2 lines, okay? So this is in the supplement section, and it is mandatory. So I'll just write this before ending the video. So there you go. So distance between Skew Lines. Skew Lines. And it's the two last videos of the supplement section of supplements playlist. Are mandatory. Otherwise, once you have watched these two videos, the lectures are done. They're finished. Okay, so don't forget. Like you have 4 applications in total. The fourth one is to be watched on the supplement section. So hopefully this helped. So I'm sorry again for these makeup classes. It was a little bit out of my control, but there you are. They're done. So congratulations and study hard for the final exam and ask me questions, of course.